Okay, so this is part 10 of our Unit 1 video, and here we're going to start looking at graphing. So the very basics of graphing, we have our x-axis, our y-axis, and the spot where they intersect is called the origin. The quadrants are numbered quadrant 1, 2, 3, and 4. And then we're going to be referring to ordered pairs or coordinates in terms of x and then y. So the first number will be the x value, and the second number will be the y value. When we first learn how to graph a new type of function, we typically use what's called the point plotting method. That's essentially choosing x values, plugging them in, and finding the y values and plotting those points. When we are finding the x-intercepts of any function, our y value is going to be equal to 0, and then our points are going to be of the form a number and then 0 as our y value. And they are on the x-axis is where our graph crosses the x-axis. Another term for x-intercepts are roots, solutions, or zeros. Y-intercepts are found by plugging in 0 for x, and they're of the form 0 and then a number for y. These are on the y-axis, and it's where the graph crosses the y-axis. So the first type of function we're going to look at is a circle, and this is the standard form for a circle. The center is at the point hk, and the radius is r. So on the end of the equation, you're going to have r squared. So for example, if this is 9, then the radius is 3. Similarly here, we have a negative on each the h and the k. So if this says x minus 3, the x value of your center is positive 3. If it said plus 3, then it would be negative 3. So we're going to go ahead and practice graphing a circle. First example here says to write the standard form of the equation of a circle with the center 0, negative 6, and then a radius of 10, and then to graph it. So first off, if our h is 0 and our k is negative 6, then we can plug those into our equation. Our r value is 10, so we can also plug that in. So if the general form for the equation is x minus h squared plus y minus k squared equals r squared, then we can go ahead and plug in h 0 and k negative 6, and we'll have x minus 0 squared plus y minus negative 6 squared equals 10 squared. And simplifying that, we're left with x minus 0 is just x, so x squared plus a negative times a negative will be y plus 6 squared equals 100. So that's the equation. And then we want to go ahead and graph it. Well, we know the center is at 0, negative 6, so 0, negative 6. And then we want to go out 10 in each direction, since that's our radius. So I'll go out 10 this way, 10 this way, 10 this way, and 10 this way. And we'll go ahead and draw that circle. And there's our graph. The next example says to find the center and the radius and the domain and range, and we're going to be looking at a graph with the equation x plus 3 squared plus y minus 1 squared equals 4. So my center is my hk, and remember, if this is a plus 3, then it's negative 3 here, and then 1 as my k value. My radius, well, if r squared is 4, then my radius is 2. I can go ahead and graph now. Negative 3, 1, 2, 3, and 1. And then I'm going to go out 2 in each direction. So up 2, to the right 2, to the left 2, and down 2. And that's my circle. It also asks for our domain and range. Now, from earlier videos, hopefully you remember that domain is our possible x values, range is our possible y values. And by looking at our graph, we can see our domain and range. Our domain, our first, if you look at the whole x-axis here, our x values go from negative 5 to negative 1. Our range goes from negative 1 all the way to 3. And we'll use brackets here because our graph actually equals -5 and it actually equals -1. It's not like it gets really close but never touches it. It does actually equal it. Now we're going to talk about domain and range a little bit more in detail here. These next terms here are going over that. So a relation is any set of ordered pairs or equation or graph. It's any relationship between two variables. The domain is all of the possible x values, or our input. The range is all of our possible y values, the output. And then the function is a function is a relation where each member of the domain matches with only one member of the range. In other words, no two ordered pairs have the same x value but different y values. And we'll use f of x to represent what's called function notation. We can also talk about the independent and dependent variables. Independent variable typically is x, that's the input, and we can pick x values to plug in. The dependent variable is the y value, it's the output, and it depends on what x is. So we're going to look at some examples here of finding domain and range from a set of points. If I have a set of points here, x and y values, and I want to find the domain and range, the domain is all of our possible, or all of our x values. So 1, 2, 3, and 4. And my range is all of my y values. 6 again, 8, and 9. I only need to list 6 once. And the way we determine if it's a function or not is if our x values have, if they repeat, essentially, if the x value matches with different y values. So here I have 1 matches with 6, 2 matches with 6. That's okay. In fact, all of the y values could be 6. They could all be the same and that would be okay. It's that I can't have 1 match with 6 and 1 match with 7. I can't have the x value match to 2 different y values. So this is a function. And we can look at the next example here. And here we have our domain and our range. Our domain is 6, 6, 8, and 9. And I don't need to list the 6 twice. My range is 1, 2, 3, and 4. And here's a good example of where we have something or a function that is, or I guess not a function, but a relation that is not a function. Notice here that my x values, 6 matches to 1, and 6 also matches to 2. Because the same x value matches to 2 different y values, that makes this not a function. All right, so here we have the vertical line test. And what we're going to be looking at here is drawing vertical lines all through this function. And if any of these vertical lines hits the graph of the function more than once, oh, I just realized you can't see what I'm pointing at here. Sorry about that. So again, vertical line test. What this is telling us is if any vertical line intersects the graph at more than one point, then the graph does not represent a function. So this is another way of using a graph to determine if something is a function or not. So what we're going to be looking at is if I draw a bunch of vertical lines, think about infinitely many vertical lines through this. If even one of those vertical lines hits my graph more than once, then that makes this not a function. So if I draw vertical lines all the way through this graph, and even though it looks like it's vertical there for a long time, it's actually not. All of these vertical lines only hit once. So this is in fact a function. Now this next one, we have the vertical line right here in green. Let me just kind of make that a little bit clearer here. This is the line we're looking at. I could draw vertical lines over here and it doesn't hit at all. Over here it doesn't hit at all. But if I draw this vertical line, not only does it hit more than once, it hits at every single point. Because it hits more than once, it is not a function. Now this next one, if I draw a vertical line over here, that's fine. Vertical line over here, that's fine. Vertical line right on the edge here where it only touches once, that's fine. But as soon as I have a vertical line that hits my graph in 2 places or more than once, then that makes this not a function. All right. So now what we're going to be looking at is functions that are a little bit different. We're going to be looking at some graphs here, and we're going to be talking about the domain and range of these graphs. So we're going to be looking at some graphs and looking at the domain and range. Now, I've kind of made a note here on this first example. It says, assume there's an open hole at g of 4, so at an x value of 4 at the end of my function there's an open dot, and a closed dot at negative 4. So at negative 4, this is a closed dot. Now looking at this graph, it ends here and here. It doesn't keep going off to infinity. And when I'm stating my domain and range, looking at my domain, again, you should be thinking x values. For a range, you want to be thinking y values, the output. And so for my x values, if you look at your x-axis here, this function goes from negative 4 all the way to positive 4. There are no x values outside of those values. It does in fact equal negative 4, but it does not equal positive 4. So my domain then would be negative 4 to positive 4 and a parenthesis on positive 4 since it's an open dot and a closed, or a bracket because it's a closed dot. My range is similar, but you're talking about the y-axis. So on the y-axis, this function goes from negative 8 to positive 8. And from negative 8 has a closed dot, and at positive 8 has an open dot. So a bracket from negative 8 to positive 8. This next graph is called a piecewise function. It's two different functions and taking part of each of them and then putting them together on the same graph. So this is a linear function, and this is a quadratic function here. And they're pieced together here. Again, it's called a piecewise function. It doesn't really matter to us that this is a piecewise function. We can still state the domain and range. Again, my domain is the x values. So looking at the x-axis here, the very first x value I have is here at negative 9. And it's a closed dot there. And then I have x values all the way until we get to 1 here. And then it's undefined there. It's an open dot there. It's also an open dot here. So we don't have the value of 1. So my first interval here from my domain would be from negative 9 all the way to 1. A parenthesis at 1 because it does not actually equal 1, but a bracket at negative 9 because it does equal negative 9. From 1, it continues to go on, and this is an arrow that's saying it's going on forever and ever and ever. So even though it's going this way really slowly, it doesn't stop. It just keeps going and using further and further x values. So from here, we'll be going from 1 to infinity. I used a parenthesis on the 1 because it's an open dot there, and then it goes all the way to infinity. We always use parentheses on infinity. Now the range we approach in a similar way, but instead of looking at the x-axis, we're looking at the y-axis. So you always want to be thinking about domain and range from least to greatest. So looking at my y-axis thinking least to greatest, if this arrow is going down forever and ever and ever, I'm never going to hit that bottom value. So going from least to greatest, we're coming from negative infinity all the way until negative 3. It's an open dot there, so we'll use a parenthesis on negative 3. And then there are no y values all the way until we get to 0. So then we have 0, and that'll be a bracket because it has a closed dot all the way until 5. And that'll be a parenthesis because it has an open dot. Our next example is part of a parabola. This ending arrow here keeps going forever and ever and ever, up, 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 but the graph ends right here. So if I'm stating my domain and my range, my domain, well, thinking from least to greatest, negative infinity all the way to positive infinity, it keeps going further and further and further this way forever and ever and ever. So our domain is going to be from negative infinity all the way until 1, and we'll have a bracket on 1 because it does equal 1. My range, if you're thinking least to greatest, there's no y values, no y values, no y values, and then we have a y value at 0. And it does in fact equal 0 here. So we'll have a bracket, and then my range keeps going up and up and up and up and up forever and ever and ever, all the way to infinity. So that would be my domain and range for that graph. One more, and this time we're going to be looking at an equation. And when we're looking at an equation and stating the domain and range, we want to look at what type of equation it is and what the restrictions are. Now there's two things I notice. One, I have a square root, and two, I have a fraction. Now first off, we know we can never divide by 0. So the value that would make my denominator 0 here is 3. If I have 3 minus x, plugging in 3 here would make this 0. So I know right off the bat, x cannot equal 3. Now the other restriction I notice is that we have a square root. And we know that we can't take the square root of a negative number when we're working with just real numbers. So I know that whatever's inside the square root, in this case 3 minus x, is going to need to be greater than or equal to 0. Now in this case we know it can't be equal to 0 because that would be dividing by 0. We already talked about that. So it can't actually be equal to 0. It's going to have to be strictly greater than 0. Well, if I solve this, if I add x to the other side, 3 is greater than x. You could also write this as x is less than 3. And from here, we can go ahead and notice that x cannot equal 3, and this kind of takes care of that. This is not equaling 3. This is strictly less than 3. So if you think about this graphically, that would be an open dot at 3. Again, it does not equal 3. And all the x values less than 3. So that would be negative infinity all the way to 3 with a parenthesis at 3. And that is my domain. And that's a good stopping place for this video. So we're going to go ahead and stop here, and then we'll pick up on page 31 with the next video.